We just finished talking about how we figure out reaction rate laws and reaction orders, and we've seen that the concentration of reactants often affect how fast a reaction occurs. Generally, the more of a reactant we have, then the faster the reaction occurs. And this is one of the factors involved, the concentration. And that was what we were focusing on when we looked at reaction rates in our previous lecture. But we also have other factors that affect reaction rates. And the factors that affect reaction rates are summarized by collision theory. Collision theory that says that we have three conditions that must be met for a reaction to occur. The first one is that the molecules must collide. If I have molecules that are going to form a new compound, then that's my first step, right? They have to be able to touch each other or encounter each other. The next thing is that these molecules must be oriented so that the reactive centers, the parts that need to react, can encounter each other. So if I have a particular location on this molecule that is going to bond with some other molecule, then only if they collide where the two parts are actually going to encounter each other will this reaction occur. If instead, this is my reactive center and this is how they hit, then this center cannot reach the part where it needs to react, and so that reaction isn't going to occur. The third factor is that the molecules must be energetic enough. Because every reaction is going to have a certain energy barrier that's associated with it. If you're breaking a bond, that requires energy. Even when you're forming a bond, your two molecules are approaching each other and there is a repulsion happening because they have electrons on the outside of them and they have this electron cloud, and so those electron clouds make this negative charge coming at each other, and if they don't have enough energy to overcome that repulsion from their electric charges and their electric fields, then they're not going to be able to get close enough to each other to react. So we already talked a little bit about concentration, right? That if we think about concentration effects, so if I'm thinking about the concentration of my reagent, then if I increase the concentration, then there's more particles that are available to react. And so, it seems like that first requirement, that the molecules must collide, is probably going to be more easy to overcome, more easy to meet that requirement. And if I also have more material, more molecules, then the odds of one of them being oriented appropriately so that a reaction occurs is probably higher if I have more of the stuff. But this doesn't really address the third requirement. So instead, this third requirement is probably most affected by the temperature. Because we know that when we increase the temperature of particles, we increase their kinetic energy. And so if we increase their kinetic energy, then not only are they probably going to collide more, so that's also going to affect it, It's probably not going to do very much about the orientation, although more collisions mean more possible times when the molecules might be oriented correctly, and so that also is going to affect it. But then our particles also have enough kinetic energy that maybe more of them are going to be able to overcome whatever energy barrier is. So we talked a little bit, I said that the rate constant, K, is constant for a constant temperature. But as soon as we start changing the temperature, we have a new rate constant. And we can describe the temperature dependence of the K using the Arrhenius equation. The Arrhenius equation is K is equal to prefactor capital A, which we'll explain in a minute, exponential function to the minus E sub A over RT. So all the details here. This is the temperature in Kelvin. R is the gas constant. Probably it's going to be in joules per mole Kelvin. And then E sub A is the activation energy. And for the units to work out, then this is going to be in joules per mole. So that way this whole term becomes unitless. This is the exponential function. This is, depending on where you look, sometimes it just gets called the prefactor. Sometimes it gets called the collision factor. Sometimes it gets called the frequency factor. So depending on which book you read, you're going to see a variety of different terms for it. Now, one thing I want to point out is that the units for the rate constant are going to be the same as the units for that prefactor A. Okay, so if we think about what's going into that prefactor A, A is going to be related to the total number of collisions, the fraction of the collisions. I should make this into a list. One moment, I'll make it into a list. 1, total number of collisions. 2, fraction of the collisions with correct orientation. And so these two requirements, right? This was the requirement number 1 from the collision theory. This was the requirement 2 from the collision theory. So the prefactor, this reflects both of those two expectations. And then this whole exponential term, this is the term that gives us the fraction of the particles with enough energy to react. So this is our requirement 3. So all 3 of these requirements that were in collision theory come into the equilibrium constant through the Arrhenius equation. So just like with the integrated rate laws, right now the Arrhenius equation looks a bit unfriendly. Like, what do we do with this? I mean, we don't really know how to get A. We don't really know how to get the activation energy, the temperature. Okay, we can actually measure the temperature. So that's one thing that we can actually get a handle on. But these other parts, this form of the equation is kind of an unhelpful form. And so just like we did when we talked about the integrated rate laws, we can do some math to this equation to make it a little bit friendlier for us. So let's go ahead and do that math. So the math that we're going to do, I'm going to rewrite the equation just so we can see the whole process here. I'm going to move that A factor over. So just a little algebra. And then I don't really know what to do with this exponential function, but I know I can get rid of it. So I'm going to take the natural log of both sides because the natural log undoes the exponential function. So then on the left-hand side, I have the natural log of the equilibrium constant over A, which I know I can separate out, right? That was that trigonometric identity we already talked about. And then the natural log and the E just go away, so I have minus E sub A over RT. Now, let me think about the variables that I might be paying attention to. I said that the K values, the equilibrium constant values, they depend on temperature. So if I remember graphing rules and sort of the fundamental idea of a function, I just said that K depends on temperature, which means that K is the dependent variable and T is the independent variable. And now I know what to graph, right? So very early on in your math, you probably were told that the dependent variable was on the y-axis and the independent variable was on the x-axis. I totally don't have a memory of learning this, but I relearned it later on. So we're going to graph natural log of k as our y-axis and 1 over t. I know this looks awkward, but this is actually a totally normal thing for us to do in math and science. And so we're going to graph the natural log of k, and these k values we can measure, and then the temperature we can measure. And if we get some of these values, then they should actually give us a straight line relationship when we look at this form, right? This might not sort of say to you immediately, oh, this is the form of a line. But pretty soon you will learn to see these. So what we're really seeing is that here is y. This guy needs to move over here and be b. And this is mx. Y is equal to mx plus b. Natural log of k is equal to minus e sub a over rt plus natural log of a. So on this graph, all of a sudden, my slope is this minus the activation energy over r. This is my intercept, which if I have a few data points, then I can graph it and I can get a y equals mx plus b. And now this value a that I didn't know how to deal with, I can just get from graphing. This activation energy that I wasn't sure how to get, I can just go ahead and pull out of the graph. So this is a really functional way for us to take experimental data like equilibrium constants and temperatures and get some additional theoretical values out of it. It's super handy. So let's go ahead and look at some rate constant data as an example. Let's look at the decomposition of yet another nitrogen oxide. We have 2 dinitrogen oxide molecules, and they are being decomposed, maybe in a catalytic converter or something, into dinitrogen and oxygen. So nitrogen and oxygen gas, just like we're turning an air pollutant into something that is just part of the atmosphere. So woohoo, it's a good reaction. So if we measure the equilibrium constant at several different temperatures, this is in Kelvin already, so we don't need to do any conversions. Our units for the equilibrium constant, just to keep track of them, is 1 over molar seconds. So if you want to pause for a second and think about what that says about what order this reaction is, it'd probably be a good exercise. It doesn't actually come into the rest of this problem, but just, since we're keeping track of those bits of information. So these are gaseous reactions that happen apparently at very hot temperatures. So these were measured at 1125 Kelvin. and we get 11.59. And then at 1053, we get 1.67. At 1001 degrees, we get 0.381, or excuse me, 0.380. And at 838 Kelvin, we get 0.0011. So you can see that as we increase the temperature, our rate constant increases just like we were thinking. So I want you to pause the video right now and open up Excel, and I would like you to plot natural log of K on your y-axis and 1 over T on your x-axis, and then get the equation for the line. And then we'll come back together in a minute, having gotten that much information out of your plot. Okay, so hopefully you got a graph that looks a lot like this one. You may not have taken time to go ahead and put labels on your graph, and if you didn't, that's totally okay. But the numbers hopefully will match up okay for you. So when we look at this graph, we can see the equation for the line right here. So this is my slope, this is my intercept, and I can go ahead and analyze it using my equations. So since natural log of A is equal to B, then I can calculate A, that would be e to the 29.346. So if you go ahead and plug that in, it'll be 5.6 times 10 to the 12th. This is a pretty high number. We're at high temperatures though, and so we would have lots of collisions, so this seems pretty smart. Our units are going to be the same as what we had up above, so that was 1 over molar seconds. And then our activation energy, well, we know that our slope is minus E sub A over R is equal to M. So if we plug in minus 30317 and you solve for E sub A, you should get 252 kilojoules per mole for your activation energy. When we get to this point, we've talked about collisions. We've talked about the importance of temperature in governing how many collisions are occurring and how we get reaction rate constants out of our equations. And so this is kind of identifying our two main factors that affect reaction rates, just to kind of sum up. And one of them was concentration, and the second one was temperature. But it is also worth adding in here an additional factor. It's not always a factor, which is why we aren't going to include it in our list of major factors. But the additional factor that can affect reaction rate is catalysts. And catalysts are a special material that speed up the reaction because they provide a different reaction pathway. That's lower energy. So they make the reaction go faster. We're going to see catalysts coming coming in as we start talking about decomposition of ozone. But for right now, I'm actually going to talk about these reaction pathways a little bit more. So reaction pathways are the actual process that the reaction takes from the reactants to the products. We may write a reaction sort of in one step. That doesn't mean it actually happens in that one step. So when we have reactions, we can kind of write the overall reaction. But then when we think about how a reaction actually occurs, We describe this as a reaction mechanism. And I'll show you an example of a reaction mechanism anyway in just a minute. So this reaction mechanism is how, like, what steps a reaction actually goes through. But the thing about reaction mechanisms is that we can't predict these. And mostly we can't observe them. Because, we can't actually see molecules interacting with each other. So we often have a hard time proving whether or not this is really how a reaction goes. Now, does that make them useless? No, not really, because what we can do is we can set up clever experiments where we can predict whether or not the reaction will be sped up under certain circumstances that help us prove how the reaction, or if not prove, help us defend the reaction mechanism so that it's not just a hypothesis, but it becomes a theory. So we need to do one additional definition before we get into some examples. And this definition that we need is elementary reactions. So elementary reactions are reactions that happen exactly as written in one step. And we have three kinds of elementary reactions. If we have a reactant and it goes and makes a product just by itself, right? It's just sitting there and then it decomposes. Or maybe this happens by photolysis or something. Anyway, there is one reactant and it makes a product, or it can even make multiple products. This is called a unimolecular reaction. And the rate for this would be controlled purely by the concentration of A. There would be no other factors involved in it. So the next way that you could have this reaction occur, you could have two different reactants reacting, or you can have two of the same. It doesn't really matter. The idea is the same here, but we have two particles that are reacting. So we call this a bimolecular reaction. And just like in the unimolecular reaction, our rate would be controlled by the reactants that are present. And it's controlled in the stoichiometry that we have listed here. So, for example, in this first reaction, we have one-to-one stoichiometric ratios here for A and B. And so the concentration of A and the concentration of B are both represented in this reaction. Here, we just have two A particles colliding together to turn our material into some product. And so we have this A squared to reflect that stoichiometry as well. So the stoichiometry of the rate law always matches the stoichiometry of the equation, which is not always true in reaction rate laws overall. So our third and fairly uncommon possible way of having reactants occur is where you have three particles. Maybe they are all different, maybe not. I'm not going to write down all three possibilities here. This is called a termolecular. I don't know why it's not tri, but anyway, it's not. It's termolecular elementary reaction. And the rate here does the same thing. A, B, and C all react together. Maybe I will just 2A plus B is a possibility. I suppose you could have 3A, but whatever. So you have three particles colliding simultaneously to make our products. Now, anything more than three particles colliding simultaneously is extremely unlikely. In fact, so unlikely that we basically say it's impossible. Even having three particles interact simultaneously, like not in sequence, but boom, three things interacting all at the same time is extremely unlikely. And so by far, number two is our most common form. We almost always have two particles that are colliding. And it's usually not more than 2. And it's usually not a single one by itself, although sometimes it is. So let's go ahead and look at an example problem here to illustrate the reaction mechanisms and the elementary reactions. So the reaction that we're going to look at here is 2 nitric oxides plus bromine gas turning into 2 BrNO. All right, so with this reaction, we're pretty sure that in our first step, 1 bromine gas molecule interacts with 1 nitric oxide molecule to establish an equilibrium with Br2NO. So they sort of just join together. In the next step, Br2NO reacts with the other nitric oxide and forms the product, 2BrNO gas. And if we add these two together, we will notice that this BrNO cancels out with this other BrNO, and we get the exact stoichiometry, this net reaction that we had right up here, which is good because that's what it has to do. So let's talk about this Br2NO for a second. Notice that the Br2NO gets produced at the end of the step 1. It gets used up at the beginning of the step 2. So this is called a reaction intermediate. And you can always tell a reaction intermediate because it gets produced at the end of a reaction or of a step early on, and then it gets used up in a later step so that it does not appear in the net reaction. It's not a net product. We can see that these two steps, step 1 and step 2, both involve 2 particles colliding with each other. So both of these elementary reactions are bimolecular. I did mention that they were the most common type, right? And when we are talking about these, we often use these steps to explain overall rate laws and reaction mechanisms. So if one of the steps in the reaction mechanism is slower than the rest, then it's going to be the rate limiting step. Imagine, for example, that I'm making pizza. I have one oven. I preheat it to the temperature that I need to bake it at. 425 is what I use. That's Fahrenheit degrees. And then I put together a pizza. So I spread out my dough, I put on all my toppings, I put on my cheese, and then I bake it in the oven. So when I put it in the oven, my timer goes on for about 15 minutes. Now that one pizza's in the oven, I can start making another pizza. But it probably only takes me maybe 5 or 6 minutes to bake or to assemble a pizza. So the baking of the pizza is my rate limiting step. I can assemble a bunch of pizzas, but I can only bake them one at a time. So I end up sort of with this equilibrium of unbaked pizzas as part of my reaction intermediate. I start with my, I don't know, maybe I want to write a reaction mechanism for my pizza, right? Just because it's funny to me. So I have my ingredients. I put them into a raw pizza. That's my step 1. And this is a fast step, relatively speaking. Ooh, I can't even spell today. What just happened there? Let's rewrite that. Ingredients. So the raw pizza encounters heat, and it turns into, yay, pizza we can eat. Not that we couldn't eat the raw pizza, but we can eat it. Great. This is the slow step. This is my rate limiting step. I can only make pizzas as fast as I can bake them. So let's look back up at this reaction mechanism above in our example. From step 1, we said this was an elementary step, so we can write the rate using the stoichiometry that's written. When we write these equilibrium steps, we need to note that that forward reaction has a rate constant K1. The reverse reaction, we say, has a rate constant K minus 1, and they are not always the same. So we're going to label both of them. And then my second reaction has rate K2, and I'm just labeling them that to match with step 1 and step 2. So rate 1 forward is going to have a rate constant of K1. Stoichiometry is Br2 and NO multiplied together. And this is also equal to the reverse reaction rate, which is that other constant, times my product. In step 2, the rate of this step is K2 Br2NO NO. We don't have the information in this setup yet to know whether step 1 is fast and step 2 is slow, or whether it's the other way around. So we don't have the information that we need to know which one is our rate limiting step, although we can hazard a guess that it's probably step 2, but we'll deal with it in a little bit. Let's look at another example instead. In this example, we're going to have more of that smog gas reacting with another gas, air pollutant, carbon monoxide, nasty stuff, making nitric oxide and carbon dioxide. Arguably, this right-hand side is maybe less nasty than the left-hand side, but they're both not great. So if this were an elementary reaction, there's only 2 particles reacting, so it could theoretically be, right? Then the rate would be K NO2 CO. But is it? It turns out no. In actuality, the real rate law for this experiment is really a rate constant times NO2 squared. The experimental rate constant being different than the stoichiometry of a chemical reaction is actually one of our first cues that we might have this reaction happening in multiple steps rather than in single steps. Another cue is if you have what looks like a super simple example, like these 2 reactants colliding, it shouldn't take a really long time for this reaction to happen if this is happening in an elementary step, necessarily, right? And as a result, if it is significantly slower than it sort of looks like it should be, that also might be an indication that we might need to look for additional steps in a reaction mechanism. So through trial and error and controlling variables carefully, we think that the reaction mechanism for this is really that in the first step, we have 2 nitrogen dioxide molecules colliding with each other, making an NO3 and an NO. And then in step 2, we think that that NO3 is reacting with the carbon monoxide that's present, and that it's regenerating 1 nitrogen dioxide and then producing the carbon dioxide. And we are pretty sure that this first step is therefore the slow step, since its stoichiometry matches the one that we actually measure. And so this second step must be fast. Remember that just a minute ago we were looking at this reaction where we said that this first step for the Br2 reacting with nitric oxide was a equilibrium. And what often happens is that when we have a slow step happening second or happening in the middle of a reaction mechanism, it often sets up a fast equilibrium right before it. If you think of my pizza example again, I had ingredients, I was assembling my pizza, and then if you think about my kitchen, I have one pizza in the oven, and now I have an equilibrium of ingredients present on my counter and also an assembled pizza ready on my counter to go into the oven as soon as the next, the previous one comes out of the oven, then I can pop a new pizza into the oven. So that's sort of a fast equilibrium step that happens right before that slow and rate limiting step. So we can imply then that what's happening in this previous reaction mechanism is probably a fast step in step 1 and a slow step in step 2. I'm going to go ahead and start another example just to have a fresh look and follow it all the way through for how we would handle it. But you can go back and do the same process with that previous example that we just were talking about. So this new example that we're going to look at is more air pollutants. This time the nitric oxide is just reacting with oxygen in the atmosphere, and it's making nitrogen dioxide. So this would be part of the smog cycle again. And it's believed to proceed through 2 steps. Nitric oxide reacting with the oxygen, making a fast equilibrium, and making this interesting reaction intermediate. And then in the second step, the reaction intermediate reacts with our other nitric oxide slowly, or at least more slowly than step 1, and produces 2 molecules of nitrogen dioxide. At any rate, it is this step 2 that is the rate limiting step. And I said that when we have the rate limiting step, this always determines the rate law. So that means for step 2, I need to write the rate law as this. And that's perfectly fine, except there's one big problem. The big problem is this right here. Reaction intermediates are fleeting. They don't hang around that long, and it's hard to measure the concentration. And so it's not very helpful to us for us to have a reaction intermediate in our rate law. In fact, we just avoid it. So we can use a little bit of math. We're going to use a little bit of algebra and what we know about equilibria in order to make a substitution. So we'll write the rate law for our equilibrium reaction. And remember that the stoichiometry is we have to pay attention to both directions. And the power of the equal sign here points out that we can solve for the concentration of this OONO just by dividing out that other rate constant. And then we can make a substitution into this rate law because this is exactly the same number. The amount of OONO at the end of step 1 has to be the same as the amount of OONO at the beginning of step 2. These two numbers are equal to each other, so we can go ahead and make this substitution. So solving for OONO concentration from our first reaction, we're going to get these two rate constants multiplied by those two concentrations. So we'll substitute that back in, and we will get that our rate law really is K2 multiplied by these K1 over K minus 1 NO O2 multiplied by that NO that was left over here. And generally speaking, we don't usually calculate these all separately. We're just going to have them all be combined in the overall rate constant. So we can simplify this as NO squared multiplied by O2 multiplied by the rate constant. And that's going to be the overall rate law. And the nitric oxide and the oxygen are both things that we can easily measure. They are reactants, and so this is not a problem for us to be able to do this math. Now we are ready to go ahead and do some practice problems, and then we're going to be all prepped to talk about ozone in a little more detail. So go ahead and do the assignment number 9, which I will be posting on the Moodle.